Thank you, Dr. Santosh. That was a very interesting session and lot of new knowledge, I'm sure, for many of our viewers today. There have been quite a few questions from our audience. We hope you can spare some time to answer a few of
Sure.
those.
Sure.
So, the first question I'm going to take up is relating to the basic topic of hydrogen storage
Mhm.
and transportation. So, what are the principal concerns associated with design of any storage or transportation medium container for hydrogen gas, given its reactivity and specifically the main concern is flammability?
Yes. So one of the primary facts that one needs to take care in designing any material for such transportation application is that the material has to be light and should be able to carry a good amount of volumetric density of hydrogen under high pressures. So since hydrogen has a low volumetric density, the enhancement of its storage in terms of the material choice would play a significant role. And apart from being able to store hydrogen uh, in a greater volume in a less space, it is also important to make sure the material is light enough so that when integrated into the transportation application, it doesn't increase the weight of or reduce the mileage or the capacity of the vehicle altogether. So, and the material should also be able to sustain any kind of impact in terms of an accident or any unintended ruptures or damage that is caused due to various reasons that may come up eventually unknowingly as well. So these are some of the important aspects that one need to focus on while designing the material, especially for transportation application.
Uh, Thank you, Dr. Santosh. The next question I want to take up is related to the mechanical properties. A lot of the slides have discussed on the stress strain characteristics and drop testing and impact testing, that kind of. But there's another thing called hardness.
Yes.
So, in terms of the cylinders your group has fabricated, have
Mhm.
you tested the hardness on a standard scale such as Mohs or any such?
Yes, we have tested the hardness, but I have not shown the results here. When we talk about the hardness, it is the strength of the material that will eventually come into picture because, as I said, when you compare the material with that of metal and the HDPE polymer, there are significant differences in terms of the hardness. Metal is more hard and brittle as well. It has a tendency to undergo hydrogen embrittlement while interacting with hydrogen, whereas the polymeric material, being light in nature, has no option or doesn't react with hydrogen at any point of time. So in these aspects, even though there is a difference in the hardness, the deformation that or the displacement that the HDPE polymer undergoes as a liner material will not cause any undue disturbances in the material development or the cylindrical liner fabrication, but in fact helps in accommodating hydrogen in an effective manner within the cylinder.
Thank you, Dr. Santosh. My next question is on the mixed matrix membranes, which are described for hydrogen separation from gas mixtures. So, could you comment on the average lifespan and compositions of the ones you have tested and observed,
Yes, the
and
composition.
uh,
Yeah.
cost efficacy as well?
Yes. So compared to the palladium-based membranes, of course, palladium is very expensive in nature. As an alternative to costly palladium, we used MgNiO2, magnesium nickel oxide nanoparticles as an alternative. And comparatively, the cost per se, magnesium nickel oxide is much lower in cost and easy to prepare compared to the use of palladium and its cost. On the other hand, in terms of the lifespan and the durability of the membranes, these membranes are quite durable. We have tested these membranes in various organic solvents, which lasted up to 1 month at the laboratory scale in about 11 different solvents, and proved to be very stable without undergoing any deterioration in spite of subjecting it to 1 month. But on an industrial scale, we would expect such membranes to last for anywhere between 3 to 5 years, so that the industry also doesn't have to really replace the membranes quite frequently, which would also incur a lot of cost for the industry. So keeping that in mind, we are optimizing the membranes to such an extent that it will be durable for 3 to 5 years.
Thank you. As a related question, in terms of the efficacy of these membranes, does the level of impurity or acidic gases due to varying origin, we have green hydrogen, blue hydrogen, black, so they contain various levels of impurity. So do they affect the longevity or operational aspects of these membranes?
Yes, there are possibilities that such impurities may affect the longevity or durability of the membrane. However, the kind of membranes that we are fabricating will be able to overcome all these disturbances and the impure effect of impurities on these membranes, so that they are rugged enough to have a sustained balance in a toxic or a complicated environment, in order to retain the difficult atmospheres and their effect on it.
In your testing, since in some of these generation processes, hydrogen is generated along with other gases. So once it goes through the membrane, is there a loss? Are you able to separate 100% of the hydrogen, or is there a loss? What level of purity is achieved when you get it from?
In terms of separation efficiencies, we were able to separate out 95% of hydrogen that is uh, produced as part of a mixture or a gaseous mixture. So 95% is quite a good separation efficiency, which can also be enhanced slightly up to 99%. So that can be industrially viable option, where almost every hydrogen molecule that is available will be able to be separated out of the mixture.
Right. Thank you, Dr. Santosh. My next question is related to the hydrogen evolution reaction and oxygen evolution reaction electrocatalyst comparison slides which you had put up. So, what are the test conditions there? Basically, I'm talking about electrolyte, how the cell was sealed, the method of measuring the gas output, and Faraday or Coulombic efficiencies.
Yeah, so we carried out these HER-OER studies at a laboratory level using a small lab scale setup, where we used nickel foam as the substrate for coating the electrocatalyst on the surface. And using nickel foam as a substrate, we were able to use a suitable electrolyte, either in the acidic form or in the alkaline medium, depending on the requirement. But in this particular case, we were able to use acidic electrolytes, so that the kind of reaction would be very minimal on the surface compared to the alkaline environments.
So, this question is related because many of the young researchers working on these kind of catalyst design, they often have this query that what is the best agreed, accepted method to measure the gas output that comes out in such kind of cells at the lab scale?
One of the best ways is to either do a GC analysis on real-time basis, in order to get to know the percentage purity of hydrogen that is coming out. That would be an ideal mechanism.
Right. Thank you, Dr. Santosh. For the next question, it's related to the cobalt selenide and graphitic carbon nitride composite material. So as I understand it, in that work there is a photocatalytic dye degradation application, an
Mhm.
energy storage application, and electrocatalytic OER HER generation was investigated. So the role of cobalt selenide here, does it add only to photocatalytic properties, or does it also contribute to the energy storage and electrocatalytic performance?
It does contribute significantly to both electrocatalytic and energy storage apart from photocatalytic activity, because we also compared the efficiency as an individual material, cobalt selenide alone, graphitic carbon nitride alone, and a combination of this as a composite material. So when compared to the other two individual materials, the composite proved to be a better material because of the complementary properties of both cobalt selenide as well as the graphitic carbon nitride. So both were contributing to a certain significant effect in order to enhance the efficiency of the material and its application.
Thank you, Dr. Santosh. Moving on, the next question we had was related to the four types of cylinders based on the lining materials that were
Mhm.
described in the slides.
Mhm.
Can you quickly comment on the thermal insulation properties of the four types? Because I could see there were different materials there. One has a glass lining, the other is a plastic lining, some use a composite. So,
Mhm.
because there is a transportation element involved, so
Mhm.
thermal insulation might also matter.
Yes, that is a very good question because when you compress hydrogen to a higher pressure of 350 or 700 bar, because of the higher level of compression, there is a significant amount of heat that is generated within the cylinder. So the material should be able to absorb the heat produced during the compression and be able to withstand the heat and the pressures at high levels. So both in the metal as well as the polymeric materials, they are capable of holding up the heat that is generated. However, because of the excessive heat produced, there may be chances of the liner material undergoing rupture. But at the same time, because of the presence of the carbon fiber that is providing extra strength to the liner material in case of type 4, that is polymeric HDP material overwrapped with carbon fiber, the rupture of the material doesn't happen actually. But in terms of metallic cylinders or repeated cycles of usage, there may be possibilities of hydrogen embrittlement due to which there may be breakage or rupture of the cylindrical material.
Thank you, Dr. Santosh. My next question is related to the ribs that were described in your manufacturing and
Mhm.
simulation process. How did you determine the dimension and regularity? Because I could observe the ribs were in some kind of
So the ribs were customized to suit the size of the cylinder. So from within the cylindrical liner material, we were able to uniformly place in such a way that equal amount of strength is given onto the liner material from within the cylinder in order to balance the kind of displacement or the rupture that it may undergo during pressure or mechanical stresses.
Thank you, Dr. Santosh. As a last question, when the ribs are being added to the storage containers, does that change the pressure levels at the micro level inside the container? And also, by adding ribs, does that increase the vulnerability of expansion?
No, it doesn't increase the vulnerability of expansion. Rather, it provides greater strength to the liner material to sustain the heat and the pressure that it is undergoing during any kind of displacement or stressful environment. And the micropores possibility do not exist here because the ribs are created during the printing itself. And in order to cover up to the micropores, we are providing an external thin metallic liner, which will eventually cover the pores that are created during the printing process, and eventually prevent the diffusion of the gas.
So thank you, Dr. Santosh, for answering our questions today. We'd like you to deliver some closing remarks to our audience who might be working in this field today, and if they have any further questions or queries. So,
Yeah. Thank you so much. I thank ACS for providing me this wonderful opportunity. And the kind of questions that the audience posed were also quite interesting. And it was also a learning aspect for me to think from a different perspective on various aspects of this research that we are continuing and pursuing. And I would love to interact with the audience who are interested to discuss further about our research work, and we are open for collaborations as well. So in case if somebody is interested, they are free to contact me by email, and we can discuss furthermore. So this is a wonderful area which has a bright future and prospects, and people can definitely take it in a positive direction to make sure that such a technology is realized in the near future. Thank you so much.